Before we can consider the time complexity of insertion, removal, and finding in a binary search tree, we have to talk about the concept of tree height. So first, let's talk about the concept of the height of a node in the tree. So the height of a node in the tree is the longest distance, in other words, we're counting number of edges to define distance, from that given node to any arbitrary leaf. So out of all possible leaves it could go to, it's the longest distance from that node to a leaf. So in yellow, let's mark down the heights of each of the nodes here. 9 is a leaf, so the distance between 9 and a leaf, in terms of counting number of edges, the longest possible distance is 0. 9 is the leaf, so there are no edges between 9 and a leaf because it is a leaf. So the height here is 0. 8, the only leaf below it is 9, and the path from 8 to 9 has 1 edge, so the height of 8 is 1. 7 has 2 leaves below it. It has 6 and it has 9. The path from 7 to 6 has 1 edge. The path from 7 to 9 has 2 edges. Therefore, the height, it's the longest of these distances, which is 2. Out of all possible paths to a leaf, we take the longest one. And then 5 has 3 leaves below it, 1, 6, and 9. The path from 5 to 1 is distance 1. The path from 5 to 6 is distance 2. And the path from 5 to 9 is distance 1, 2, 3. The largest of these is 3. So the height of 5 is 3. And then 1 and 6 are leaves, so just like with 9, their heights are 0. If you think about this, we can actually think of a simple algorithm for computing the heights of every single node. We could theoretically do a post-order traversal where if the current node is a leaf, its height is 0. Otherwise, if it's an internal node, its height is 1 plus the largest height of any of its children. So here, 9 is a leaf, so its height is 0. 8 is not a leaf, therefore its height is 1 plus the largest height of its children. Its only child has a height of 0, therefore its height is 1 plus 0. 6 and 1 also have heights of 0 because they're leaves. 7 is an internal node, so its height is 1 plus the height of its largest child's height. So its 2 children have heights 0 and 1. So the larger height is 1, so its height is 1 plus 1, which is 2. And then same here, its children have height 0 or 2. 2 is the bigger one, so its height is 1 plus 2, which is 3. So pretty easy to do visually, and it's actually a fairly simple algorithm to implement. So that's how we compute the height of the nodes in our tree. What about the height of the tree overall? We define the height of a tree to be the height of the root of that tree. So for this entire tree, the height of the tree is the height of the root, which is 3. So we say this tree has height 3. We can start to describe time complexity with respect to tree balance. So we can think of tree balance as being this metric of how tall a tree is with respect to the number of nodes it has. And we can think of it kind of as a spectrum. So given some n, some number of elements, number of nodes in my tree, I can think of tree balance as being a spectrum between perfectly unbalanced and perfectly balanced. So here I have 2 binary search trees, both contain the exact same elements. The number is between 1 and 7. But here I have a perfectly unbalanced tree, where the height here, 1, 2, 3, 4, 5, 6, is 6. So the height of this tree is 6, versus here it's the exact same elements, also a valid binary search tree, but the height here is 2. So in general, as the number of elements grows, the height of our tree must also grow. If I have more elements, I must have more edges to connect them. But a perfectly balanced tree minimizes the height of the tree with respect to how many elements it contains, versus a perfectly unbalanced tree maximizes the height of the tree with respect to the number of elements. So these are both binary search trees, And we can think about how fast or how slow a find, insert, or remove algorithm would be. So remember, all three of those algorithms, the first step is performing the find operation. So that is actually the rate limiting step of all three of those algorithms. For a perfectly unbalanced tree, I have 7 nodes, and my height is 7 minus 1, which is 6. So in general, if I have n nodes, n elements, a perfectly unbalanced tree will have height equals n minus 1. It's essentially just a linked list where I have n nodes, and I have an edge connecting them in a chain. So the height would be n minus 1. Therefore, the worst case big O time complexity for find, insert, or remove would be big O of n. In the worst case, I would have to traverse over all of the edges of my tree, and I have big O of n edges in order to find the element, or find the site of insertion, or find the removal site. So for example, let's say I want to remove 7 from this tree. Removing 7, I would start at the root. 7 is bigger than 1, traverse right. 7 is bigger than 2, traverse right. 7 is bigger than 3, traverse right. 7 is bigger than 4, traverse right. 7 is bigger than 5, traverse right. 7 is bigger than 6, traverse right. Oh, 7 is equal to 7, I can remove it. So for remove, I had to traverse big O of n edges. For find, I had to traverse big O of n edges. And for insert, let's say I wanted to insert 8 into this tree. I would do the exact same big O of n find operation and then just insert here. So the worst case, in a perfectly unbalanced binary search tree, all three of my operations are big O of n. In a perfectly balanced tree, my height is 2, which this is actually log base 2 of n plus 1 minus 1. It might be a little complicated how I just kind of pulled this out of the top of my head. Don't worry about it. Just think, if I almost doubled the height of my tree, so if I added if I almost doubled the number of nodes in the height of a perfectly balanced tree, if I almost doubled the number of nodes in a perfectly balanced tree, I would add one more row of 1, 2, 3, 4, 5, 6, 7, 8. I would add 2 children to each of the bottom row. My tree currently has 7. I would add 8. I've essentially doubled the number of nodes in my tree, but my height would increase by 1. So you can maybe think about this a bit more to see how we would derive this function, but with n equals 7 nodes, it's log base 2 of 8, which is 3, minus 1, which is 2. So in a perfectly balanced tree, our three operations are big O of log n, right? This is the dominant term. However, this is not the worst case scenario. This is not the worst case. This is actually a very nice case. This is the case when my tree is perfectly balanced. So the worst case time complexity for a binary search tree in general is big O of n. If my tree was perfectly balanced, the worst case time complexity would be big O of log n. But for a just general arbitrary binary search tree, I'm not guaranteed that it will be perfectly balanced. So for some general binary search tree, this big O of n term is what you want to remember as the worst case time complexity. In the future, we will talk about other binary search tree data structures that are what we call self-balancing. And these self-balancing binary search trees do give us a guarantee of some notion of tree balance. But just in general, for an arbitrary valid binary search tree, we have no such guarantees of height, therefore the worst case is big O of n. Let's talk about the best case, worst case, and average case time complexities of the find algorithm of a binary search tree. In general, the best case time complexity happens in our best case scenario. Oh, and generally speaking, these are given n elements. So we have n elements where n approaches infinity. So the best case time complexity is the best case scenario, which for a binary search tree find is when the query, what we're looking for, happens to be the root. So here, if I'm searching for node 1, the first node I check is the root, which is what I'm looking for, I succeed. Here, if I'm looking for node 2 is the root, so immediately I succeed. And here, the very first node, if I'm looking for 3, I would find it immediately, so I would succeed. So the best case time complexity for a binary search tree is big O of 1, regardless of what the shape of my tree is. And even if I have some large n elements, I will always find it when I check the root. So the best case time complexity, regardless of how large the input size is always just constant time, no matter what my tree shape is. The worst case time complexity, I have to think of the worst possible scenario, which for the case of a binary search tree would be a perfectly unbalanced tree. So this tree and this tree, the two perfectly unbalanced trees here, are the worst possible scenarios for my binary search tree find algorithm. So in this tree, if I looked for the element 4, I would theoretically have to traverse over big O of n edges before I fail. And here, if I was looking for the element 0, similarly, I would have to traverse over big O of n edges before I fail. So the worst case scenario for a binary search tree is if my tree is perfectly unbalanced and I didn't find it, or equivalently, if it was the last element. This would be big O of n. What about the average case time complexity? This is something that we don't talk about too often, but this is what we would theoretically expect. So this is the theoretical expectation. It's an actual statistical expected value over all possible scenarios we might face. So over all possible trees and all possible queries, it would be the expected value. And just to remind you, this is the expected value equation. So for some random variable capital Y that can have any value lowercase y, the expected value of capital Y is lowercase y times the probability that capital Y variable equals that lowercase y over all theoretically possible values lowercase y. This seems a bit abstract, but we'll dive into it a little bit slowly for a binary search tree. We'll talk about what assumptions we have to make and how we can actually do some form of a theoretical expected value over binary search tree shapes and queries. In order to explore the average case time complexity of finding an element in a binary search tree, I first have to make two simplifying assumptions. First, I will assume that all n elements that are in my binary search tree are equally likely to be searched for. So let's say I have a binary search tree containing the numbers 1, 2, and 3. This would mean that the probability that my query is 1 is the same as the probability that my query is 2, is the same as the probability that my query is 3, which generally speaking would mean each of their probability is 1 over n, which in this example, I have 3 elements, so 1/3. So I'm assuming if I have n elements, the probability that I'm searching for any specific element is 1 over n. The second simplifying assumption is that all n factorial possible insertion orders are equally likely. So given n elements, I can pick any of those n elements to be the first one to insert. Then out of the remaining n minus 1 elements, I can pick any of them to be the second one that I insert. Out of the remaining n minus 2 elements, I could pick any of them to be the third element to insert, etc. So the number of possible insertion orders, how many different orders I can actually insert n elements, there's n factorial possible ways, and I'm assuming each of those is equally likely. So for this example, where I have the numbers 1, 2, and 3, let's take a look at those possible scenarios. So I could do 1, then 2, then 3. So that would be 1 is the root. Then I insert 2, that would be the right child of 1. Then I would insert 3. Oh, 3 is greater than 1. 3 is greater than 2. That would be the right child of 2. I could do 1, 3, 2. So 1 is the root. Then 3 is greater than 1, so I would make it the right child of 3. Then 2 is greater than 1, so I traverse right. It's less than 3, so it's the left child of 3. I could have 2, 1, 3. So 2 is the root. 1 is less than 2, so it becomes the left child. 3 is greater than 2, so it becomes the right child. I could have 2, 3, 1, which starts with 2 as the root. 3 is greater than 2, so it's the right child. 1 is less than 2, it's the left child. I can have 3, 1, 2. So I first insert 3, then 1 is less than 3, so it's the left child of 3. And then 2 is less than 3, but it's greater than 1, so it becomes the right child of 1. Or I could have 3, 2, 1. So 3 is the root, then 2 is less than 3, so it's the left child of 3. Then 1 is less than 3, and it's less than 2. So it would be the left child of 2. So given n equals 3, I have n factorial equals 3 factorial equals 3 times 2 times 1 equals 6 possible insertion orders, each of them being equally likely. Notice that I'm not saying that all possible trees are equally likely. On the contrary, we see that these two different insertion orders gave me the exact same tree. When I insert 2, then 1, then 3, versus when I insert 2, then 3, then 1, I get the exact same tree. I'm not saying all trees are equally likely. I'm saying all insertion orders are equally likely. So in this example, I have 1, 2, 3, 4, 5 unique tree shapes, but this tree shape is twice as likely as the other ones because there was 2 different insertion orders that gave rise to it. Let's also introduce the concept of the depth of a node. We will define the depth of any given node to be the number of nodes in the path from that node to the root. So, for example, in this tree, let's label all of the depths of each node. So for the root, the number of nodes from the path from the root to the root is just one node itself, right? It is the root, so the number of nodes between it and the root is itself. So just one here. What is the depth of this node? Well, there's 1, 2 nodes on the path from this to the root, so its depth is 2. For 14, there's 1, 2, 3 nodes along the path to the root. For node 13, there's 1, 2, 3, 4 nodes along the path from it to the root. Here, there's 1, 2 nodes. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3, 4. And now we've labeled the depth of every single node. So why did I just introduce this new term? Well, if we think about it, we're trying to compute the average case time complexity. So average case time complexity. It's the expected number of operations to find a query, Query. So the expected number of operations to find a query. So let's say one operation is one comparison. Let's say I was looking for the number 3. I would compare 3 with 8. Oh, 3 is less than 8. Let me go left. I would compare 3 with 3. Oh, they're equal. I've succeeded. So that would be 2 comparisons. And the average case time complexity is the expected number of comparisons or expected number of operations for every single node here, which would be equivalent to the expected depth, right? You saw that when I was looking for 3, I compared 3 against 8. Nope, 3 is less than 8. I went here, 3 is equal to 3, success. So I did 2 comparisons, and it has a depth of 2. Let's say I was looking for the number 13. 13 is greater than 8. That's one comparison. 13 is greater than 10. That's a second comparison. 13 is less than 14. That's 3 comparisons. 13 equals 13. That's 4 comparisons, which is equal to its depth. So generally speaking, the number of comparisons to find a node is equal to the depth of that node, which is why we're able to make this jump. So average case time complexity being the expected number of operations to find a query, that's just the definition. So this here is the definition. But then given this piece of information, this realization that the number of comparisons to find a node is just the depth of the node, we can now translate average case time complexity into this. It's just equivalent to finding the expected depth over all possible nodes. What is the expected depth? Well, expected depth, it's an expected value of the depth. So let's say that the depth of some given node x is d of x. The expected value of depth, so expected value of, let's say, d, is the sum over all possible nodes x of the depth of x times the probability that I'm looking, so my query is x. And remember, previously I told us that all possible queries are equivalent in terms of probability. So this is the same thing as the sum over all possible queries or all possible nodes x of the depth of that node times 1 over n, right? I have n possible nodes. They're each equally likely to be searched for. So the probability of any given node x is 1 over n. I could pull this out of my sum. So this equals 1 over n times the sum over all possible nodes x of the depth of x. This is not dx like in calculus. This is d subscript x, so the depth of x. So in other words, if I can find the sum over all nodes x of the depth of that given node, I would just multiply that by 1 over n, and that would give me my expected value. So we figured out that the average case time complexity of finding an element in a binary search tree is just the expected depth of a node in a binary search tree, which, assuming all nodes are equally likely to be searched for, is just 1 over n times the sum of the depth of all of the nodes in that tree. But there's one big issue here. This equation is assuming that I'm only looking at a specific single binary search tree. However, the expected value that I'm looking for, the average case time complexity, should be over all possible scenarios, which means all possible insertion orders. So to tackle that generalization, let's talk about what expected total depth would be. So let's define total depth. So total depth of a given insertion order j. So remember, some specific insertion order defines a specific binary search tree. So let's say that the total depth of insertion order j, one of my n factorial possible insertion orders, is dj of n. This is the total depth of insertion order j given n elements. There's n factorial possible insertion orders. This is the total depth of this specific jth insertion order. We want the expected total depth across all possible insertion orders. Therefore, I'll use a different color for this. Let's let d of n, so no subscript j, be the expected value over all possible total depths for specific insertion orders. So this would be the sum over all possible insertion orders j of the total depth given that insertion order times the probability that I actually saw that specific insertion order. So it's the total depth of insertion order j times the probability that I inserted my elements in insertion order j. But remember, my second assumption was that all insertion orders are equally likely. Therefore, this probability here, the probability that I specifically saw insertion order little j, is just 1 over n factorial. There's n factorial possible insertion orders. They're all equally likely. So the probability of this specific one is 1 over n factorial. So this becomes the sum over all possible insertion orders j of the total depth of insertion order j times 1 over n factorial. I can pull this out of my sum. So the expected total depth would be 1 over n factorial times the sum over all insertion orders j of the total depth of insertion order j. So I'll say j equals 1 to n factorial, because there's n factorial possible insertion orders j. So hopefully that follows. Let's just recap real quickly. So we said total depth of a given tree is, so the total depth of a specific tree is just the sum of the depths of all the nodes. So just real quick to make sure people are following what that means. The total depth of this tree, let's say this tree was created using insertion order. Well, let's not worry about that. So for this specific tree, the total depth is 1 plus 2 plus 2 plus 3 plus 3 plus 3 plus 4 plus 4 plus 4, right? I'm just adding the depths of every single one of these nodes. So this is 4, 8, 12, 15, 18, 21, 23, 25, 26. So if I'm doing my math right, which hopefully I am, the total depth of this specific tree is 26. So the total depth of an insertion order j is the sum of the depths of all of the nodes of the tree resulting from that insertion order. And the expected total depth is 1 over n factorial times the sum of the total depths of every single possible insertion order. Okay, so this sounds like I've just done something bad. I basically have determined our answer with respect to some n factorial sum. Do I actually have to enumerate all possible n factorial insertion orders and compute the total depth of every single one? Or can I do something to rethink this and maybe make my computation a little more efficient? So just to recap, this is what I want, but this sum is exponential. That seems too big. So can I do something faster to figure out this sum? So let's quickly recap to make sure we're all on the same page. This all started because I wanted the average case time complexity of finding a node in a binary search tree. And using assumption 1 that all nodes are equally likely to be searched for, I made this equal to 1 over n, so 1 over the probability of searching for any given node, times the total depth of a node of a tree with n nodes. So the expected total depth of a binary search tree with n nodes. If I could find this out, I would have my answer. So the expected total depth of a binary search tree with n nodes, well, using assumption 2, I figured out that I'm assuming all insertion orders are equally likely. Therefore, over all possible n factorial insertion orders, the expected total depth would be 1 over n factorial, the probability of seeing a specific insertion order, times the sum of the total depth of insertion order j over all n factorial possible insertion orders. However, this sum has an exponential number of terms in it. I don't want to have to compute this sum. So hopefully I can avoid doing this. Is there some better way of computing the expected total depth of a binary search tree with n nodes without having to do this exponential sum? Let's try to think of a general scenario. So let's imagine a binary search tree that has n nodes in it. It has a root, and let's say it has I nodes in its left subtree. If it has I nodes in its left subtree, it must, by definition, have n minus I minus 1 nodes in its right subtree. Because remember, there's n elements total, so 1 plus I plus n minus I minus 1 is n total. So let's say that let's define d of n given I is the expected total depth of a BST with n nodes total and I nodes in its left subtree. So in other words, let's let d of n given I be the expected total depth of this tree here. It has a root, and it has I nodes in its left subtree, and there's n nodes total. Let's think of this recursively. How can I define this recursively? I can actually define d of n given I as a function of d of I and d of n minus I minus 1. So this itself was a tree. This itself is a valid binary search tree. Just this subtree here. It's a valid binary search tree. It has some depth I. So d of I is the expected total depth of a binary search tree with I total nodes. This is the expected total depth of a binary search tree that has n minus I minus 1 nodes. These are just the definitions of what d of I and d of n minus I minus 1 would be. If I had these two values, I could find d of n given I, because it would be, so d of n given I would just be the expected total depth of this subtree plus the expected total depth of this subtree, plus I've added 1 to every single node in here's depth. So each node here is now 1 node further from the root, because I've added this new root. So let's say the root of this subtree, it used to have a depth of 0, but now that it's become the subtree of this overall tree, its depth has now increased to 1. Its child's depth has increased to 2. So every node in this subtree, by attaching this subtree as a child of this root, its depth has increased. So I add 1 for each of my I nodes here. So I add I in total. And similarly, each of the n minus I minus 1 nodes in this subtree now has 1 larger depth. So for each of these nodes, each of these n minus I minus 1 nodes, I've increased my total depth by 1. So I increased my total depth by n minus I minus 1 in total. Plus, my root has a depth of 1. Therefore, the expected total depth of a given tree, the expected total depth of a tree with n nodes, given that it has I nodes in its left subtree, is just the expected total depth of a tree with I nodes plus the expected total depth of a tree with n minus I minus 1 nodes plus, so this cancels out with this cancels out with this, plus n. So how can I use this to solve my answer? Well, basically, what is the so the expected value, so d of n, which is what I'm looking for, it's this term, d of n equals the expected value over all possible i's. So this is the sum over I equals 0 to n minus 1. I have a root, therefore the smallest number of nodes I can have in my left subtree is 0. That would be if all my nodes were in my right subtree. Or the largest value is n minus 1. That means that I have no nodes here. So all nodes other than the root are in my left subtree. So the sum from I equals 0 to n minus 1 of d of n given I times the probability that I have I nodes in my left subtree. So it's the expected total depth of a tree with n nodes and I nodes in its left subtree times the probability of having I nodes in your left subtree. So again, I've introduced an unknown term. What is this? If I had this term, probability of having I nodes in my left subtree, I would be able to solve this, which means that I would be able to solve this, which means that I would be able to solve this. So what is this term? Probability, so let's reiterate. So this is the probability of having I nodes in my left subtree. This may seem confusing at first, but think about what dictates having I nodes in your left subtree. That means that the root is the I plus 1 largest element. If I have n elements total, if I have I nodes in my left subtree, that means that the root is the I plus 1th largest element. So for example, let's say I have 3, 2, 1, and 4. In this example, I equals 2. I have 2 nodes in my left subtree. This came about because the root was the I plus 1th, the 2 plus 1, or the third largest node in my tree. So it's just some specific node in my tree. And what made 3 be the root of my binary search tree? Well, by definition, the root of a binary search tree is the first node that was inserted. Therefore, this probability, the probability that I have I nodes in my left subtree, let me use a different color. This is equivalent to the probability that the I plus 1th largest, smallest node was the first to be inserted. So here, the probability of having 2 nodes in my left subtree is the probability that the third smallest, this should also be smallest. So the probability of having 2 nodes in my left subtree is the probability that the third smallest element was the first one that was inserted. But remember, assumption 2 said all insertion orders are equally likely. So out of my n possible nodes that I could have inserted first, I happen to pick this one. Well, the probability of that is just 1 over n. The probability of first inserting any of my nodes is just 1 over n, because all insertion orders are equally likely. So, to finish this off, I can rewrite this as d of n equals, this probability is just 1 over n. I can pull it out. This is 1 over n times the sum from I equals 0 to n minus 1 of this term, d of I plus d of n minus I minus 1 plus n. So let me actually rewrite that so that's all in one line. So d of n equals 1 over n times the sum from I equals 0 to n minus 1 of quantity d of I plus d of n minus I minus 1 plus n. So I'll circle this one actually. It's all in one line. And even though this equation, this recurrence relation, looks complicated, it's at least a closed form recurrence relation only depending on d of some input. It only depends on the expected total depth. This was quite a journey, but let's finish this up. So we last ended with a final recurrence relationship for d of n as a function of all these terms over here. 1 over n times the sum from I equals 0 to n minus 1 of d of I plus d of n minus I minus 1 plus n. We can rewrite this as 1 over n times the sum from I equals 0 to n minus 1 of d of I plus 1 over n times the sum from I equals 0 to n minus 1 of d of n minus I minus 1. So that's this term, plus, well, the sum from I equals 0 to n minus 1 of n, this is just adding n to itself n times. That's just n squared. Divided by n is just n. So plus n. So these two sums, it might not be obvious, but basically let's try plugging in some values. So this is d of 0 plus d of 1 plus all the way up until d of n minus 1. So that's this one here. Versus this sum here, the first value is I equals 0. So this is d of n minus 1 plus a bunch of stuff plus d of, so when I equals n minus 2, n minus 2, so n minus 2 plus minus 1. So basically when I equals n minus 2, this is just d of 1. And when I equals n minus 1, this is just d of 0. So this sum and this sum are actually the exact same sum, just solved in two different orders. This is going from 0 to n minus 1. This is n minus 1 to 0. It's the same exact sum. So we could say that this equals basically 2 over n times this sum, because they're the same thing, so just 2 over n, just multiply by 2, and then plus n. I can multiply both sides by n, so I would get, let me use a different color now. So I would get n times d of n equals 2 times the sum from I equals 0 to n minus 1 of d of I plus n squared. Then I could substitute n minus 1 for n. I would get n minus 1 times d of n minus I equals 2 times the sum from I equals 0 to n minus 2 of d of I plus n minus 1 squared. And then I can subtract this equation from the one before it, and I would get n d of n minus n minus 1 d of n minus 1 equals 2 times d of n minus 1 plus n squared minus n minus 1 squared. If I collect these terms, I can get a final recurrence relation of, let me actually use a different color for this, of n times d of n equals n plus 1 times d of n minus 1 plus 2n minus 1. And to solve this recurrence relation, I can divide by n times n plus 1 to get d of n over n plus 1 equals d of n minus 1 over n plus 2n minus 1 over n times n plus 1. And once if we basically do n equals 1, so if we have n equals 1, the base case would be d of 1 over 2 equals d of 0 over 1 plus 2 minus 1 over 1 times 2. So basically, d of 1 equals 1 because, so d of 0, so what is d of 0? D of 0 is the expected total depth of a tree that has 0 nodes. That's by definition 0. Therefore, d of 1 is 1. And then collecting my terms, I would get, let me use a different color for this now. I would get d of n over n plus 1 equals the sum from I equals 1 to n of 2i minus 1 over I times quantity I plus 1, which is the sum from I equals 1 to n of 2 over I plus 1 minus the sum from I equals 1 to n of 1 over I times I plus 1. And I can further simplify this using induction. I won't show it here, but I'll just summarize. So the sum from I equals 1 to n of 1 over I times, so this is I times I plus 1, equals n over n plus 1. So therefore, a lot of parts, but therefore, we get sum from I equals 1 to n of 2 over I plus 1 equals 2 times the sum from I equals 1 to n of 1 over I plus 2 over n plus 1 minus 2, which equals 2 times the sum from I equals 1 to n of 1 over I minus 2n over n plus 1. So the closed form solution to this, so this is finally getting to the end. The closed form solution here, d of n equals 2n plus 1 times the sum of I equals 1 to n of 1 over I minus 3n. If you didn't fully follow what just happened, don't worry about it. The math is a little complex, but it's not essential to totally follow. Basically, the last step, this is the last step, I promise. We can approximate this as d of n is basically, so this is very similar to, well, actually, so I don't think I'll do the last step. So we can approximate this to basically show that the expected value of a find operation is roughly 2 times quantity n plus 1 over n times natural log of n minus 3. How I got this, don't worry about it. There's an approximation that I made to get here, which is approximately 1.386 times log base 2 of n. All that matters to you, so if you didn't follow anything in this super lengthy derivation, all that matters is this log base 2 of n term. It's some constant times log base 2 of n. So all we care about is that this shows that this is in expectation big O of log n. Woo, we did it. So don't worry about the math if it didn't make all the best sense. The basic takeaway of this entire super lengthy mathematical derivation is that we have shown that given those two assumptions we made at the beginning, that the big O average case time complexity of doing a find operation is indeed big O of log n. It's approximately 1.386 times log base 2 of n, but all we care about in big O is that it's big O of log n. Some retrospect, so we made two assumptions. We assumed that all insertion orders are equally likely, and we assumed that we will be equally likely searching for any given element in our tree. These two assumptions are not the most realistic with real data. So under these simplifying assumptions, we get an expected value of big O of log n, but this doesn't necessarily hold with real world data.